Hello everyone, welcome to our channel. Today we're going to discuss about logic micro operations in computer architecture and organization, or we simply call it as computer organization. So in the previous class we discussed about arithmetic micro operations. So today we're going to discuss about logic micro operations. So what are logic micro operations? Okay, so actually specific binary operations on the string of bits in registers. So logic micro operations are bitwise operations, that is they work on the individual bits of data. Okay, so these logic micro operations are nothing but bitwise operators. So they mainly work on the individual bits of data. So these are mainly useful for bit manipulations on binary data. So binary means 2, right? That is zeros and ones. So it's mainly used for the bit manipulation. So how to change the bits? So if there is 1, if it is changed to 0, if it is 0, it is changed to 1. So these are bit manipulations. So next is useful for making logical decisions based on the bit value. So it is used for mainly making logical decisions based on the bit value. So there are in principle 16 different logic functions that can be defined over two binary input variables. Okay, so if we have two binary input variables, total we have 16 different logic functions. So we simply call them from F0 to F15. So 0 to 15 is nothing but 16. So however, most systems only implement 4 of these, like AND, OR, XOR, complement, or NOT. So most systems use only 4 of the logic micro operations. What are they? AND, OR, XOR, complement, or NOT. The others can be created from combination of these. So this is the basic introduction about logic micro operations. So now we'll see the list of logic micro operations. So as we said that we have 16 different logic operations, right? So we have only two binary variables. So we have only two binary variables, and we have 16 different logic operations. So if we have n binary variables, then 2 power n. So which is nothing but 2 power 2. So which is nothing but 2 power 4. So what is 2 power 4? Which is nothing but 16, right? So we have 16 different logic operations with two binary variables. So let's see a truth table for the 16 functions of two variables and the corresponding 16 logic micro operations. So what is 16 here? So 0 to 15, right? So what is 0? 0, 0, 0, 0. What is 15? 1, 1, 1, 1. So here total 0, 0, 0, 0 to 1, 1, 1, 1. So these are 15, 0 to 15, that is total 16 bits, 16 logical operations. So this is the first one is 0. So what is 0 here? That means your f naught equal to 0. So f naught equal to 0 means we are clearing everything. That means there is no information in it. So f tends to 0 is nothing but your clear operation. So that is the first logic micro operation for us. That is f naught equal to 0. That is clear operation. So here 0, 0, 0, 0. So next 0, 0, 0, 1. So 0, 0, 0, 1 is f1 equal to x, y. That is if we talk in the micro operations perspective, f tends to a and b, which is nothing but your AND operation. Okay, so the second logical micro operation is AND. So it is for 0, 0, 0, 1, that is for 1. So f1 equal to xy, that is f tends to a and b, and 2, 0, 0, 1, 0. So f2 equal to xy bar. Okay, so it's exactly opposite here. If it is 0, we have 1. If it is 1, we have 0. That is xy bar. That is f tends to a and b bar. Okay, so a and b bar. So coming to the 3, 0, 0, 1, 1. So f3 equal to x. So if we have f3 equal to x, that is f tends to a. So we don't have b here. That means we are transferring a. So the fourth micro operation is transfer a. Next for 4, f4 equal to x bar y. So x bar y in the sense f tends to a bar and b. So this is fifth micro operation. So next is 5. So for 5, we have Fy equal to Y. So if you see F3 equal to X, the same manner we have Fy equal to Y. So F tends to B. So if when F3 equal to X, we have F tends to A, right? In the same manner, when Fy equal to Y, we got F tends to B, which is nothing but exactly opposite to transfer A, that is transfer B. So next is for 6. For 6, we have 0, 1, 1, 0. So F6 equal to X XOR Y. So this is XOR symbol, right? So X XOR Y. So F tends to A XOR B. The operation is exclusive OR. So this is the 7th micro operation for us. And next, coming to 7, that is 0, 1, 1, 1. F7 equal to X plus Y, that is F equal to A or B. So this is logical OR operation. Okay. And next for 8, 1, 0, 0, 0. So F8 equal to X plus Y whole bar. So that means exactly opposite to OR. So which is a negation of OR, which is nothing but NOR operation, right? So F tends to A or B to the whole bar. Okay. So coming to the 9th operation, that is F9. So F9 equal to X or Y to the whole bar. Okay. So if we talk in the micro operations perspective, F tends to A XOR B to the whole bar. So which is nothing but exactly opposite to NOR, that is exclusive NOR. That is not negation of NOR, which is exclusive NOR. So coming to the 10th operation, F10 equal to Y bar, which is nothing but exact, see, term X as A. So let us assume X as A and Y as B. Okay. So if we say that F10 equal to Y bar, which is which means that it's B, right? So F tends to B bar. So which is nothing but complement B. So coming to the F11 operation, that is X plus Y bar. So which is F tends to A or B, right? So coming to F12, that is 1, 1, 0, 0. So F12 equal to X bar. So if F10 equal to Y bar, which is complement of B, then F12 equal to X bar, which is complement of A, right? So why? Because we termed X as A and Y as B, isn't it? So next is F13 equal to X bar plus Y, right? So now F tends to A or A dash or B. So coming to the 14th one, F14 equal to XY whole bar. So we know XY means A and B, right? So F tends to A and B whole bar, which is nothing but your NAND operation. And coming to the last one, that is 1, 1, 1, 1, that is F15. So when F15 equal to 1, F tends to all ones, right? So set to all ones. So if you observe carefully, the first 0th operation, so 0th logical micro operation is clear. So F tends to 0, right? So what is exactly here? F tends to 0 is a clear operation, and if you see the 15th operation, that is 16th operation, F15 equal to 1, which is exactly opposite to F0. So here in F0, we are clearing the entire data. In F15, we are setting all to ones. Okay. So these are the 16 logic micro operations we have here. And if you see the hardware implementation of this logic micro operations here, so here we'll take 4 into 1 multiplexer. So if we take 4 into 1 multiplexer, as we know that we'll take 2 selection inputs, right? So 2 selection inputs in the sense 2 power n, that is 2 power 2, we'll get 4, right? So we'll get 4 micro operations, so 4 operations here, and I'm taking input AI, BI. Okay. So if it is 0, 0, 0, if it is 0, 1, so you can see the table here. If it is 0, 0, that is 0. If it is 0, 1, that is 1. If it is 1, 0, that is 2. If it is 1, 1, that is 3. Okay. So if it is 1, 1, 3 is selected. If it is 1, 0, 2 is selected. You can clearly observe in the table here. So AI, BI, we need to take the inputs here. So you can see the function table over here. We have taken 2 selection inputs, right? S1, S0, and this is an output operation. This is the logic operation. So for 0, 0, we say F equal to A and B. So here we will use AND operation, logical AND. For 0, 1, F equal to A or B, that is OR operation. For 1, 0, F equal to A XOR B, we will use XOR operation here. For S1, S0 equal to 1, 1, we take F equal to A bar, which is nothing but your complement. So if you observe carefully here, AI, BI, which logic gate have we taken here? We have taken logical AND. So this is logical AND, right? So for AI, for the second one, that that is for bit 1, here we have taken logical OR operator. For 2 we have taken, so this is OR. For third one we have taken XOR operator, so XOR gate, and for fourth one we have taken complement, that is NOT. Okay, so this is the hardware implementation, and finally we'll get the output Fi. So that's what we termed in our functional table here. For 0 0 F equal to A and B, for 0 1 F equal to A or B, for 1 0 F equal to A XOR B, for F equal for 3 F equal to A bar, that is complement. So this is 0, this is 1, this is 2, this is 3. Okay, so this is the hardware implementation of logic micro operations. So now we'll see the applications of logic micro operations. So what applications do we have? And this is an important question. So in your examination they may ask like this. So explain briefly about logic micro operations, or else write the applications of logic micro operations. Okay. So as you know that the logic micro operations which we have is AND, OR, XOR and complement, right? So what are the different applications we have for logic micro operations? But here we're discussing only 4, right? So as I said, we're discussing only 4, but actually we have total 16. So how we got that? 2 power n. So that is equal to 2 power 2. So total we get 16 logic micro operations. So out of it we are discussing only 4, right? So but all the remaining 16 will have a combination of these 4. Okay, and coming to the applications of logic micro operations, logic micro operations can be used to manipulate individual bits or a portions of a word in a register. Okay, for example, if I say 1011, so what is logical micro operations application here? So I may manipulate the entire 1011 or I may manipulate either 1, either 0, either 1, either 1. So that means I can manipulate individual bits or a portions of a word in a register. For example, consider the data in a register A. In another register B is the data that will be used to modify the contents of A. So what's the concept here? So first let us assume that we have data in register A. So A has some data, and in another register B is the bit data that will be used to modify the contents of A. That means B contains the data which is the modification of A. So that is what our application is all about. So here we have different applications of logical micro operations. The first one is selective set. Second one is selective complement. Third one is selective clear. Fourth one is mask. Fifth one is clear. Sixth one is insert. And seventh one is compare. So what operation do we have for selective set here? A tends to A plus B is the operation which we get for selective set, use for selective set. For selective complement, it is XOR operation. Okay, so for the first one, selective set, it's OR operation, and for selective clear, it is A dot B bar, and for mask delete, it's A dot B, that is AND. Okay, and for clear, it is again XOR, A XOR B, and for insert, it is A dot B plus C, and for compare, it is A XOR B. So these are the different applications we have. So let us discuss each one individually right now. So the first one is selective set, isn't it? So what is selective set here? In a selective set operation, the bit pattern in B. So remember carefully here, the bit pattern in B is used to set certain bits in A. So the bit pattern in B is selected in such a way that this the certain bits in A will be changed here. So for example, here we have taken 1100 for A, okay, and for B 1010, right? So if you see the second point here, if a bit in B is set to 1, okay, that same position in A gets set to 1. Otherwise, the bit in A keeps its previous value. Okay, so what's the point here? If a bit in B is set to 1, see the first bit here, see the first MSB here, my MSB is 1. So what if bit in B is set to 1? that same position in A gets set to 1. So I am writing here 1 1 0 0 and 1 0 1 0. So this is A and this is B, right? So for B we have 1 here. So what if we have 1 in B? What exactly is present in A? We will get here. So in A we have 1, right? So straight away we will write 1 here. So if you see here, the same position A gets set to 1. Otherwise that bit in A keeps its previous value. Okay. So here we have 0, right? So no need to check here. Keep the previous value here 1. And see the third one here, we have 1. So what do we have in A? 0. So what's the point here? If a bit in B is set to 1, that same position A gets set to 1. But in the first case, we already have 1. So no need to change here, we got 1. And in the second one, we have 0 in the place of B. So no need to change in A. And in the third case, here we have 1. But in the place of A, we have 0. So what happens now? We need to change 0 to 1, right? And the fourth bit, that is least significant bit, the LSB is 0. So no need to change in the place of A. So what we get here? 111 0. Okay, I am repeating it once again. See here 1 1 0 0 and 1 0 1 0. So what's the point here? If we have 1 in B, we need to set 1 in the place of A in the corresponding bit. So here we have 1. So actually we have 1 in A, so no need to change. So straight away write 1. Next, in the second bit we have 0. So if we have 0, no need to change here. So straight away write 1. And for third bit we have 1. So what happens if we have 1? Change the corresponding bit to 1. We have 0 here, change it to 1. And the fourth bit, that is LSB is 0. So no need to change in A. So write 111 0. The same operation is performed is A tends to A plus B. So that is OR operation. So if you see the value here, if we perform OR operation, we will get selective set. So what is selective set? Basically A tends to A plus B. So what exactly is this? OR operation, right? Now coming to selective complement. So in a selective complement operation, the bit pattern in B is used to complement certain bits in A. So if a bit in B is set to 1, so you need to see the second point carefully. If a bit in B is set to 1, that same position in A gets complemented from its original value. So I am writing here 1 1 0 0, which is there for A, 1 0 1 0. So this is A, this is B, right? So what if a bit in B is set to 1? If a bit in B is set to 1, that same position A gets complemented from its original value. So this is B, right? Here it is set to 1. So what value do we have in A? 1. So we should complement this 1. So what will we get here? We'll get 0. What about second bit then? So we have second bit as 0. So if we have 0, don't change it. So directly write 1. So what do we have in 1? A, we have 1, right? So directly write 1 here. So what about third bit here? So third bit we have 1, right? So if we have 1, just complement the position of A. So here we have 0, right? So complement it and we'll get 1. So what about the fourth bit, that is LSB? LSB we have 0 here. So no need to change, directly write 0. So what we got here, the final value is 0 1 0. So what exactly is this value? It's nothing but XOR operation, right? So what is selective complement here? Selective complement is nothing but your XOR operation. So if a bit in B is set to 1, that same position in A gets complemented from its original value. Otherwise, it is unchanged. Hope it's clear for you. So and the third one is selective clear. So in a selective clear operation, the bit pattern in B is used to clear certain bits in A. So the name itself says here, so selective clear. So what bits are we going to select and what bits are going to be cleared? So if it is second point here, if a bit in B is set to 1, that same position in A gets set to 0. Otherwise it is unchanged. So the matter is very clear here. So let us take for 1 1 1 0 0. So that's for A, right? So what about B then? 1 0 1 0. So what exactly is the point here? If a bit in B is set to 1, okay, in B I have 1. So if a bit in B is set to 1, then the corresponding A should be cleared to 0. So in A I have 1, so clear it to 0. And if in the place of B, if we have a bit 0, then don't change anything. So in A I have 1, so no need to change, directly write 1. And if we have 1, in the third bit I have 1, so clear it to 0. So anyways the bit in A is already 0, so write 0 here. And if we have 0, that is LSB, we have 0 here, so no need to change anything, so write 0. So what is the output which I got here? 0 1 0 0. So the exact operation here is A tends to A dot B bar. Okay, so this is selective clear. And coming to mask operation, so in a mask operation, the bit pattern in B is used to clear certain bits in A. Okay, so see the second point here. If a bit in B is set to 0, that same position in A gets set to 0. For example, if a bit in B is set to 0, so if B has 0, then the same position A gets set to 0. Otherwise, it is unchanged. So let's take a value here, 1 1 0 0. This is for A, and 1 0 1 0. This is for B, right? So what's the point here? If a bit in B is set to 0, okay, the first bit is 1, so don't need to change anything, write 1, and the second bit is 0. So what if we have 0 here? Change the bit which is there in A to 0, so 0. And if we have 1 here, no need to change anything, directly copy 0. And for the fourth bit, that is LSP, we have 0 here. So we need to change the bit to 0, but in A we already have 0, so directly write 0. So what output we got here? 1 0 0. So what's the operation for mask operation? It's AND, A and B. Okay, so this is mask operation. Now clear operation. So in a clear operation, if the bits in the same position A and B are the same, they are cleared in A. Otherwise, they are set in A. So if you see here, if the bits in same position A and B are the same. So if you see here I have 1, here I have 1. So now clear it to 0. So clear in A. So in A it is 1, so clear it to 0. Okay. Now these two are different. So directly write the value present in A, that is 1. And these two are different again, 0 and 1 are different. Okay. So write the value present in A, that is 0. And now these two are same, 0 0 are same, right? So now write the value present in A. We have 0, right? So 0 1 0, we got 1 0 1. Otherwise they are set in A. In a clear operation, the bits in the same position A and B are same, they are cleared in A. So for 1 I will get 0, here I will get 0. So remaining cases you will get 1 1. So what I get? So 1 1 0 0 1 0 1 0. So what exactly is our operation, clear operation here? If both are same, so 1 1. Now clear the position in A. So here I have 1, so clear it to 0. So here also same, 0 0. Then what do we have here? 0, so clear it to 0. So remaining all cases you will get 1. So 1. So 0 1 1 0. So that's a clear operation. So 0 1 1 0 is nothing but your XOR operation. So now insert operation. So an insert operation is used to introduce a specific bit pattern into A register, leaving the other bit position unchanged. That is a mask operation to clear the desired bit positions, followed by an OR operation to introduce the new bits into the desired position. Okay, so this is the original bit 1101 1000 1011 0001, and the desired is the mask. So 1111 1111 1111 0000. So A is intermediate here, and these are our added bits, and this is our A desired bits. Okay, so in some textbooks there is nothing for insert operation here. So they will discuss only these 4 operations. Okay, I hope the concepts are clear. So this is all about logical micro operations. I hope you understood the concept. So if you guys have any doubts in this topic, please place your doubts in in the comment section. And the students who are watching my channel for the first time, I request you to please subscribe my channel and please share my videos to your friends who are studying in other different colleges. Please share my videos in your WhatsApp groups and please subscribe my channel and please support my channel in all possible ways. Thank you very much and have a wonderful day.